This is an original paper on the theory of quantum mechanics, the theory of quantum mechanics unraveling the mysteries of the subatomic world. Introduction. Imagine a world where the rules of reality as we know them no longer apply, a world where particles can exist in multiple states at once, where observing something changes its behavior, and where the very act of measurement defies our everyday understanding of cause and effect. This is the realm of quantum mechanics, a revolutionary theory in physics that has transformed our understanding of the universe at its smallest scales. In this paper, we'll explore the origins of quantum mechanics, its core principles, and the profound implications it holds for science and technology. Whether you're a curious learner or a science enthusiast, join me on this journey into the subatomic world, where the impossible becomes possible, the birth of quantum mechanics. Our quantum mechanics emerged in the early 20th century as scientists grappled with phenomena that classical physics, Newton's laws, and Maxwell's equations couldn't explain. Classical physics worked beautifully for large objects like planets or baseballs, but it failed at the atomic and subatomic levels. The story begins in 1900, when German physicist Max Planck proposed a radical idea to solve a problem known as the ultraviolet catastrophe. Scientists had observed that a heated object, like a piece of metal, emits light across a spectrum of colors, but classical physics predicted that it should emit infinite energy at high frequencies, an absurd result. Planck suggested that energy isn't emitted continuously but in discrete packets, which he called quanta. This idea, though initially a mathematical fix, laid the foundation for quantum theory. 5 years later, in 1905, Albert Einstein expanded on Planck's concept. Einstein used the quantum idea to explain the photoelectric effect, where light shining on a metal surface causes electrons to be ejected. Classical physics predicted that the energy of the ejected electron should depend on the light's intensity, but experiments showed it depended on the light's frequency instead. Einstein proposed that light itself is made of quanta particles we now call photons, and that a photon's energy is proportional to its frequency. This groundbreaking work earned Einstein the Nobel Prize in 1921 and solidified the quantum concept as more than a mathematical trick. By the 1920s, the quantum revolution was in full swing. Scientists like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Louis de Broglie developed the framework of quantum mechanics. Bohr's model of the atom, introduced in 1913, proposed that electrons orbit the nucleus in specific energy levels, jumping between them by absorbing or emitting quantum energy. De Broglie in 1924 suggested that particles like electrons exhibit wave-like behavior, a concept known as wave-particle duality. Heisenberg and Schrödinger then formalized quantum mechanics with two different but equivalent approaches, Heisenberg's matrix mechanics and Schrödinger's wave mechanics, the latter introducing the famous Schrödinger equation, which describes how a quantum system evolves over time. Core principles of quantum mechanics. Quantum mechanics is built on several key principles that challenge our classical intuition. Let's break them down. Wave-particle duality. One of the most mind-bending aspects of quantum mechanics is that particles like electrons and photons can behave as both particles and waves. In the double-slit experiment, for example, electrons fired at a barrier with two slits create an interference pattern on a screen, just like waves of light do. But if you try to measure which slit an electron passes through, the interference pattern disappears, and the electrons behave like particles. This duality means that the nature of a quantum object depends on how we observe it. Superposition. Quantum systems can exist in multiple states simultaneously, a phenomenon called superposition. For instance, an electron can be in a superposition of spinning up and down at the same time. This isn't just a theoretical idea, it's been experimentally confirmed in systems like atoms and subatomic particles. Superposition is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box can be considered both alive and dead until the box is opened and observed. Quantum entanglement. When two particles interact, their states can become linked or entangled, such that the state of one instantly affects the state of the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, was demonstrated in experiments like John Bell's in the 1960s, which confirmed that entangled particles violate classical expectations. Entanglement is now a cornerstone of quantum technologies like quantum computing and cryptography. The uncertainty principle. In 1927, Werner Heisenberg formulated the uncertainty principle, which states that certain pairs of properties like a particle's position and momentum, cannot be measured simultaneously with perfect precision. The more precisely you know a particle's position, the less precisely you can know its momentum, and vice versa. This isn't a limitation of our instruments, it's a fundamental property of nature, reflecting the errant fuzziness of the quantum world. Wave function and probability. The state of a quantum system is described by a mathematical object called a wave function, which encodes the probabilities of finding a particle in various states. When we measure a quantum system, the wave function collapses to a single state of process that's still not fully understood and is the subject of ongoing debate in quantum mechanics. This probabilistic nature means we can't predict exactly what will happen in a quantum event, only the likelihood of different outcomes. Implications and applications. Quantum mechanics isn't just a theoretical curiosity, it has reshaped our understanding of the universe and driven technological innovation. Here are some of its most significant implications. Understanding the universe. Quantum mechanics explains the behavior of atoms and molecules, which underpins chemistry and biology. It's essential for understanding phenomena like superconductivity, where materials conduct electricity with zero resistance, and the behavior of stars, where quantum processes govern nuclear fusion. Technological advancements. Quantum mechanics has given us technologies that define the modern world. Semiconductors, the building blocks of computers and smartphones, rely on quantum principles. Lasers, used in everything from medical devices to fiber optic communication, work because of quantum transitions in atoms. Medical imaging techniques like MRI and PET scans also depend on quantum effects. Quantum computing. Perhaps the most exciting frontier is quantum computing. Unlike classical computers, which use bits to represent information as zeros or ones, quantum computers use quantum bits, or qubits, which can exist in superpositions of 0 and 1. This allows quantum computers to solve certain problems, like factoring large numbers or simulating molecules, much faster than classical computers. Companies like IBM, Google, and startups like Rigetti are racing to build practical quantum computers, which could revolutionize cryptography, drug discovery, and artificial intelligence. Philosophical questions. Quantum mechanics raises deep philosophical questions about the nature of reality. Does the act of observation create reality, as some interpretations suggest? The Copenhagen interpretation, favored by Bohr, argues that the wave function collapse occurs upon measurement, while the many worlds interpretation proposes that all possible outcomes of a quantum event occur in separate, branching universes. These debates continue to challenge our understanding of existence itself, challenges and future directions. Despite its successes, quantum mechanics is not without challenges. The theory doesn't fully align with Einstein's theory of general relativity, which describes gravity and the large-scale structure of the universe. This incompatibility has driven the search for a theory of everything, such as string theory or loop quantum gravity, that can unify quantum mechanics and relativity. Additionally, the measurement problem, why and how the wave function collapses, remains unresolved, fueling research into alternative interpretations and experiments to test quantum foundations. Looking ahead, quantum mechanics promises to unlock new frontiers. Quantum cryptography could make communication unbreakable, using entanglement to detect eavesdroppers. Quantum sensors could revolutionize navigation and medical diagnostics with unprecedented precision. And as quantum computers become more powerful, they could solve problems that are currently intractable, from optimizing global supply chains to designing new materials for clean energy. Conclusion. Quantum mechanics is a testament to human curiosity and ingenuity, revealing a universe far stranger and more wondrous than we ever imagined. From its humble beginnings with Planck's quanta to its modern applications in technology, quantum mechanics has reshaped our understanding of reality at the smallest scales. It challenges us to rethink what we know about the world, pushing the boundaries of science, philosophy, and innovation. As we continue to explore this subatomic realm, one thing is certain: the quantum revolution is far from over, and its mysteries will inspire generations to come. So, the next time you hear about a particle being in two places at once, remember you're glimpsing the magic of quantum mechanics, where the impossible becomes reality. This is an original paper on the theory of quantum mechanics by Quantum Stellar. Please click on the link for a more detailed explanation. Thanks for watching here at Quantum Stellar. Please like and subscribe.
Thanks for watching here at Quantum Stellar. If you can, please make a small donation to this channel. They are not monetized yet and are about to go broke, folks. So get it done, and don't forget to check back for more content.
Thanks for watching, and don't forget to check back for new content. Every day we edge closer into chaos. Keep your doors locked and your head on a swivel. Hope to see you back soon. God bless.